Welcome to Math with Professor V. In this video, I'll be solving the most recent exam that I gave to my Calc 2 students this semester, and the exam covered integration techniques, approximate integration, improper integrals, arc length, and surface area. So let's jump right in. First question says, integrate the function. We have an indefinite integral of y squared over 25 minus y squared to the 3/2 dy. So right off the bat, I spot this is going to require trig sub. And I'm looking here at this quantity in the denominator, 25 minus y squared. Now remember, when you have a variable quantity and a constant, then it's going to require trig sub. And there's three cases, yes? So let's make sure we all have them straight. If you have a constant squared minus a variable quantity squared, then you're going to let y equal a sine theta. If you have addition between the two quantities, then you let y equal a tangent theta. And then this is why it's so important to pay attention to the order of subtraction. When the constant's first, you use sine theta. When the variable is first, then you let y equal a secant theta, all right? Addition obviously doesn't matter because addition's commutative, so that one always calls for tangent, all right? And here, that means we're going to use sine theta for our substitution. So I'm going to go ahead and let y equal. Now notice right here I have 25. 25 is a squared. That means a is 5. So I'm going to let y equal 5 sine theta. And then I need to differentiate both sides here. So dy would be 5 cosine theta d theta. All right. Now I'm going to substitute everything back into the integral. So I have an integral in terms of theta, not y anymore. So here we go. In the numerator, instead of y squared, I'm going to have 5 sine theta squared. And then in the denominator, I have 25 minus y squared. Well, that's 25 sine squared theta to the 3/2. And then remember, dy is equal to 5 cosine theta d theta. So that gets tacked on right here. 5 cosine theta d theta. All right, now we call in the cleanup crew and we go, let's clean this bad boy up before we integrate. So numerator, that should be good. That's just 25 sine squared theta over. Now, down here, I can take a 25 out of both terms in the denominator, and then I have 1 minus sine squared theta, and that's all being raised to the 3/2 power. Yes? Good. And then times 5 cosine theta d theta. Very good. Now I want us to focus our attention down here just for a little bit. The whole point of doing trig sub is so that you can use your Pythagorean identities to simplify inside the integral. So this 1 minus sine squared theta, I'm going to replace with cosine squared theta, and I still have this 25 out here. And remember, all this is being raised to the 3/2 power. So how does that simplify? If you need a little refresher, whatever the denominator is on this exponent, you take that root of the quantity here, and then you raise it to the numerator. So basically, we're taking the square root of 25 cosine squared theta, and then we're going to raise it to the 3rd power. We're going to cube it. And then when we take the square root, technically this would be absolute value of cosine theta, but remember in trig sub, we restrict where theta can be, so we don't have to worry about keeping absolute value and this, that, and the other. So just carry on, footloose and fancy free, and this is going to turn into 5 cosine theta quantity cubed. Okay, so let me rewrite in the next line what we have. I have, be careful, 25 times 5 in the numerator, so that's 125 sine squared theta cosine theta d theta over, and then now I have 5 cosine theta cubed. Well, 5 cubed is going to be 125. And then cosine theta cubed, I can just write it like so. Oh, well, this is very lovely because notice the constants cancel out. We love when that happens. And also I can cancel out one of the cosine thetas. So now I just have cosine squared in the denominator. So that leaves us with integral sine squared theta over cosine squared theta d theta. Well, we must just jump to rewriting this as tan squared theta. I mean, what other choice is there? And then you pause maybe for a half a second and you go, do I know the antiderivative of tangent squared theta? No, we do not. So what do? We use a Pythagorean identity. We replace tan squared theta with secant squared theta minus 1 d theta. And then now we can proceed because yes, we most certainly know antiderivative of secant squared theta is tan theta minus antiderivative of 1 would just be theta, and then put plus c right here. Are we all right? Yes, so you see it is so crucial that you have all your derivatives, antiderivatives memorized, because otherwise you would just sit here and be like, I don't know, do I know this antiderivative or don't I? How should I proceed? But immediately I go, oh no, tangent squared, nope, that's not one of the ones that we have right off the bat, so let me use a Pythagorean identity. Okay, then we have to go back to the original variable of the problem, which was y. How do we do that? Go all the way back to where you first decided to do a trig sub. Did it feel so long ago? I know. So y equals 5 sine theta, right there. I'm going to copy that down below. Y, I need a pen. Y was equal to 5 sine theta. Isolate the trig function. So y divided by 5 is sine theta, and now we're going to draw a triangle that represents this. So sine of theta should equal y over 5. That should be opposite over hypotenuse. And then we can use the Pythagorean theorem, find the missing side. It would be, very good, square root of 25 minus y squared. And then now I can use the triangle to rewrite the integral in terms of y. So tangent of theta would be ratio of opposite over adjacent. So that would be y over rad 25 minus y squared minus, and then what about this plain old theta? Well, you come over here where you isolated the trig function right before the triangle. Theta all by its lonesome is sine inverse of y over 5. Okay. Plus c. Don't forget the plus c. You need to put plus c immediately. So as soon as you have taken the antiderivative here, you see, I have no more integral sign, I have no more differential. It needs to be there every step of the way until the final answer. Okay, that's it. That was the first one. They did really well. Moving on. Express the integrand as a sum of partial fractions and evaluate the integral. So I told them, please use partial fraction decomposition for this problem. And they did. So here we go. Let's find the partial fraction decomposition of the integrand first. So we have 6x squared plus x plus 45 over, I can factor the denominator. All I can do is take out an x, and then you're left with x squared plus 9, right? X squared plus 9 does not factor further. It's an irreducible quadratic. It's prime. So our partial fraction decomposition will have the form a over x plus bx plus c over x squared plus 9. Very nice. What's the next step? Right, we're going to multiply through by the LCD. So multiply by x squared plus 9. And then now we're going to have 6x squared plus x plus 45 equals a times x squared plus 9 plus bx plus c times x. And then from here, I'm just going to distribute everything on the right-hand side. So we have 6x squared plus x plus 45 equals ax squared plus 9a plus bx squared plus cx. And to solve for the coefficients, I'm going to set the to solve for a, b, and c, I'm going to set the coefficients of like terms equal to each other. So what do I mean? The highest power of x I see in this whole equation is 2, right? X squared. So the coefficient of x squared on the left-hand side is 6. And then I have a plus b x squareds on the right-hand side. So that tells me 6 must equal a plus b. Then keep going. So x to the first, coefficient of x to the first on the left-hand side is just 1. And then all I have is cx on the right-hand side. So that means 1 has to equal c. Okay. And then lastly, our constants, or x to the 0. What do we have going on here? We have a 45 equals 9a. 45 equals 9a. So I already know c is 1. This tells me now that a is 5. And if a is 5 and I go back to this first equation, then that means b has to be 1. So now I've solved for all my constants. Isn't that fabulous? Okay, so we can rewrite our integral now as 5 over x plus 1x plus 1, because c was 1, over x squared plus 9 dx. And then from here, we're going to split up the two terms here in the numerator because we're going to have to deal with each of them differently. So we'll have 5 over x plus x over x squared plus 9 plus 1 over x squared plus 9 dx. All right. Now, some of my students were just able to go from here to the final answer, and I have absolutely no problem with that. I think that's fabulous. Others broke it up into 3 little baby problems. So I'll do that right now just in case you need to see a little bit more work done to get to the final answer. But just know that if you're pretty comfortable and advanced with your integration techniques, you should be able to just go to the final answer from here. But anyways, we'll call this integral 1, 2, 3, and we'll put them all together. So antiderivative of 5 over x dx, do you know what that is? This is number 1. Yes, it's 5 ln, don't forget the absolute value of x, plus, I'm going to put c1. That's our first little constant. Second, we have x over x squared plus 9 dx. Now, how do we deal with this? Well, notice here I have x squared plus 9 in the denominator, and then I have x to 1 degree lower in the numerator. So this is a prime time to use u substitution. Anytime the degree of the numerator is 1 lower than the denominator, and you just have one term, then u sub will work out nicely. So let's see. If there's a bunch more terms, blah, 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 then it's more complicated than we do partial fractions. But if it's just one lonely guy, it's u sub time. So we can let u be the whole denominator, x squared plus 9. And then du would be 2x dx. Do you see how lovely? Because derivative of 9 is 0. So when you're doing u sub, always throw your constant in there. It'll make life nicer. And then we have 1/2 du equals x dx. Okay, so if I put this all together, now my integral becomes 1/2 du over u. So this is 1/2 ln absolute value of u plus c2, which is 1/2 ln. Now u is x squared plus 9, which is never negative. So I can actually just switch to putting regular parentheses for that, plus c2. Okay, so I have integral 1 done, integral 2 done. Now on to integral 3, which takes almost no work at all. Some students, they were so in the zone, they forgot their minds and they did a trig sub, which would get you to the right answer. It certainly would, but it's a lot more painful. So just recall, okay, when you have integral 1 over x squared plus a squared dx, it's 1 over a tan inverse x over a plus c. But a few of them, they just were Maybe they wanted to show off how good they were at trig sub, and they trig subbed to get there. So we have 1/3 tan inverse x over 3 plus c3. Okay, and then I'm going to put it all together. You know, I ran out of space because look at me writing so much, having a grand old time with you guys. So we have, or all together, we have 5 ln absolute value of x plus 1/2 ln x squared plus 9 plus 1/3 tan inverse x over 3 plus c, and then where this new c is c1 plus c2 plus c3. And we're done. Beautiful. I actually told them this problem was going to be on the test. They didn't, I switched up the numbers. They knew that. But I said, please make sure you can do this problem. And they did, for the most part. Okay. Shall we move onward? I think so. Okay, approximate integration. So, find an upper bound for the error using the trapezoidal rule in estimating the integral from 2 to 5 of 1 over x minus 1 squared dx with n equals 4 steps. And I gave them the formula for the error bound for the trapezoidal and midpoint rules. I don't allow calculators on my exams, so I didn't put any questions in where they would actually need to compute like the midpoint rule with 10 subintervals or something like that, because it's not really feasible without a calculator. So just these kinds of questions are what I put on there. All right, so we're going to use the formula right here, error for trapezoidal rule. Okay, and let's set everything up. So that's going to be less than or equal to k times. Now, what are a and b in this problem? Well, you look at the limits of integration. So b is 5, a is 2. So 5 minus 2 cubed over 12 times, and then n is 4. That's given to me, 4 squared. So really what I need to do now is figure out what k is. And also here, that's given. So k is an upper bound on the second derivative of your function. So what is my function? Look again at the integrand. F of x is 1 over x minus 1 squared. And since I'm going to take a couple derivatives, right away let's rewrite this as x minus 1 to the negative second. Get it in derivative-friendly format. Pronto, please. So let's take two derivatives. F prime of x is going to be negative 2 over x minus 1 to the negative third. And then second derivative is 6 times x minus 1 to the negative fourth. Okay, now I want to look at the absolute value of this second derivative. So I'm going to rewrite it now as 6 over x minus 1 to the fourth. And I'm noticing I don't need to put absolute value bars because the numerator is positive, and then the denominator is being raised to the fourth. So that's not going to be negative ever. I want to find an upper bound for this second derivative on the interval a to b, on 2 to 5, okay? Now there's a couple ways you can do this. I could take a third derivative and then using our Calc 1 techniques, identify the absolute max of the second derivative. So remember, if you take one more derivative, that helps you find mins and maxes. So if I want the max of the second derivative, I would take the third and find the absolute max on this closed interval. That's more work. It's not a lot of work on this one, but another thing you can do, if you just kind of want to cut to the chase, I love cutting to the chase, is you go, hey, this numerator is not changing, right? Only the denominator is changing. If I plug in 2 minus 1, that's just going to be 1, okay? And then as I move through the interval, as I plug in larger and larger numbers, this denominator becomes larger and larger, right? Like if I plug in 5 minus 1 to the fourth, 4 to the fourth, what is that, 256, right? So then if the denominator is getting bigger as I move through the interval, that means this whole quantity is getting smaller. So the second derivative is decreasing on 2 to 5, and I didn't take another derivative to observe that. I just looked at it. So then I know this will achieve its absolute max when x is 2 at the beginning of the interval. So I could say this is always going to be less than or equal to 6 over 2 minus 1 squared, which is just 6 on that interval, okay? So we're going to use k equals 6. K is just an upper bound on the second derivative. It's not necessarily the max, right? An upper bound just has to be something that bounds that derivative or that function from above. The function may never even achieve that value. There's a difference. Okay, so let's proceed using k equals 6. So error, trapezoidal rule. We put absolute value because we're interested just in the magnitude of the error. Like how much are we off? We don't care if it was in the positive or negative direction usually. So we have 6 times 5 minus 2. What's that? 3 cubed over 12 times 16. And then yes, they have no calculator. So we're just going to cancel. This becomes a 2. 3 cubed, that's 27. And then 2 times 16 is 32. And that's the final answer. You leave it like so. Okay? Very good. One more having to do with approximate integration. And again, I just did some error-bound problems, okay? So estimate the minimum number of subintervals. That means we're finding n, okay? Needed to approximate the integral from 0 to 1 of 18 cosine x dx with an error of magnitude less than 10 to the negative 5th using Simpson's rule. And then here I gave them again the error bound for Simpson's rule. I don't make them memorize that. And also just a reminder that when you do Simpson's rule and you're finding k, it's an upper bound on the 4th derivative, interestingly enough. Okay. So I did doctor this problem up a little bit and I told them that way it would come out nicely with no calculator. So let's proceed. So basically what we want in this problem is for our error, this is the expression for our error, we want it to be less than 10 to the negative 5th. So we want k times b minus a to the 5th over 180 n to the 4th. We need that to be less than or equal to 10 to the negative 5th. You have to set up the direction of this inequality correctly. This is an upper bound on the error, and I need this upper bound to be less than 10 to the negative 5th. So you know, this is how it really all goes together, okay? That's important. Let's plug in everything that we have so far. I don't have k yet. B minus a, there's b, there's a, so it's just 1 minus 0 to the 5th over 180. They don't know n, they're solving for n, has to be less than or equal to 10 to the negative 5th. All right, now how to find k? It's an upper bound on the 4th derivative. So f of x here is 18 cosine of x, okay? Let's go ahead, let's take 4 derivatives. So f prime of x would be negative 18 sine x. F double prime of x would be negative 18 cosine x, good. F triple prime, positive 18 sine x, good. And then the 4th derivative, why, we're right back where we started. Oh my goodness, that's no coincidence, 18 cosine x. Well, what's an upper bound for 18 cosine x on the interval from 0 to 1? And I'll take absolute value of that 4th derivative. Well, let's think here. 18 cosine x, and we're on the interval from 0 to 1. I mean, regardless of what interval we're on, cosine x at most is equal to 1, right? If we imagine the graph of cosine x, it's bounded between negative 1 and 1. So the biggest this can ever be is 1. So I can say for sure this is less than or equal to 18 times 1, which is 18. So that's what I'm going to use for k. We're going to use k equals 18. And then you'll see why this is going to work out so beautifully right now, okay? Look at Professor V always looking out for her students. So we have 18 times 1 to the 5th over 180 n to the 4th. is less than or equal to 10 to the negative fifth. Now, hold on, get rid of this. I need some space. If we cancel 18 and 180, I'm just going to have a 10 down here, yes? Okay, so I have 1 over 10 n to the fourth is less than or equal to 10 to the negative fifth. I'm going to multiply n to the fourth to the other side. So 1/10 is less than or equal to 10 to the negative fifth times n to the fourth. To get rid of 10 to the negative fifth, if you divide by 10 to the negative fifth, that's the same as multiplying by 10 to the fifth over 1, excuse me. So this would cancel. And then we would have 10 to the positive fifth in the top over 10 is less than or equal to n to the fourth. Well, 10 to the fifth over 10, that's just 10 to the fourth is greater than, or is less than or equal to n to the fourth. Then we take the fourth root of both sides, and n has to be greater than or equal to 10. And for Simpson's rule, n must be even, but it's already even, so we're good, we're done. See how nicely I worked out the numbers? I'm running out of space because I just gave myself 1 page per problem, but don't worry, when I photocopy the exam for them, they have 1 page front and back per problem. Okay, how was that one? Good? Now, if n had come out to be 9 or something, then you would always round up to the next even integer when doing Simpson's rule. Okay, time for some improper integrals. So determine whether the improper integral converges or diverges. If it converges, find its limit. So first thing we need to do is rewrite this improper integral using a limit. I made sure I did tell them it was improper just in case they didn't notice. What makes it improper? This lower limit being 0, because e to the 1 over x squared would be undefined, as well as x to the negative third, because that's 1 over x cubed. So I have to rewrite this now as the limit. Usually we'll use a dummy variable like t or a. T approaches 0. It's going to be from the right-hand side because we're approaching the lower limit. Remember, this integral goes from 0 to natural log of 4. So the only way to approach 0 is from the right. So we put a plus sign. That's important for when we take the limit later, okay? Then you go from t to natural log of 4, x to the negative third, e to the 1 over x squared dx. Okay, from here, let's focus on evaluating this integral. Some of them just did a little separate problem off to the side as an indefinite integral. Fabulous. Others kept the limits and just worked with it from here. So I'll do that. I'm noticing right off the bat, we're going to need to do u substitution. I'm going to let u be the exponent, 1 over x squared. Okay, so let u equal 1 over x squared, which remember, that's x to the negative second. So then du is negative 2x dx. So then du is negative 2x to the negative third dx. So let's see, we've got negative 1/2 du equals x to the negative third dx. Perfect. There's x to the negative third dx. I love it. And so we have the limit as t approaches 0 from the right. I'm going to switch my limits of integration right now. Just give me 1 second. We're going to have negative 1/2 e to the u du. Now the limits I have to switch as well because currently they're in terms of x and I need them to be in terms of u. So let's substitute them in. Just ask yourself, who do these limits belong to right now? They belong to x. So I'm going to plug them in for x to figure out what the new limits are in terms of u. So u of t would be 1 over t squared. So that goes down here. And then u of natural log of 4 would be 1 over ln of 4 squared. So that's my new upper limit. Okay. Good. Now, antiderivative of negative 1/2 e to the u, we can do that, no big deal. Nothing happens with the negative 1/2. It's just a constant. Leave it alone. And then our antiderivative is going to be e to the u from 1 over ln of 4 squared to 1 over t squared. Now, some of my students, they're so slick. Do you know what they did? They didn't even write that step out. They, quick as lightning, rewrote this as limit t goes to 0 from the right. They made it a positive 1/2 e to the u, and then they switched those limits. 1 over t squared, 1 over ln of 4 squared. I love it. The more cleaned up it is, you know why it's good? Less of a chance you're going to make a mistake, right? So, I mean, they've wowed me the past couple months. Okay, now, onward and upward, limit t goes to 0 from the right. Keep that 1/2 outside. Then you're going to have e to the 1 over t squared minus e to the 1 over ln of 4 squared. Okay. Now, let's take this limit. As t goes to 0 from the right, do you know where 1 over t squared is going? Shall we investigate this limit? Limit t goes to 0 from the right, 1 over t squared. That's going to positive infinity. The denominator, when it's going to 0, and it's through positive values because it's squared, and we're going to 0 from the right. If this is going to 0 and the numerator is a positive constant, everything goes to infinity. If you forgot, then you can review your limits at infinity. I have a whole video. Also, you remember the graph of 1 over t squared or 1 over x squared? Looks like this. So whether you're going to 0 from the right or from the left, both sides go to positive infinity. Okay, so what does that tell me? This little exponent here is going to positive infinity. And then e raised to something getting very, very large. Again, think of the graph of e to the x. It's like this, more or less, okay? So if e is being raised to something very, very large, it's also getting very, very large. So this whole term right here is going to positive infinity. Minus. Now, no, I'm very sorry. These can't cancel. It's so tempting, but no. This entire natural log is being squared. So if you forgot, if you have ln of 4 squared like this, don't do anything. Please stop. Control yourself. If you have ln of 4 squared and the squared is only being applied to the argument, then you can write this as 2 times ln of 4. Do you see the difference? It's so dangerous. Students always get this jumbled up. You're not alone if you wanted to do something like that. But, oh, you must have restraint, okay? There, that's the danger box. So anyways, no, we're not touching this. We're just leaving it alone. I don't know what it is. We don't have a calculator in my class, so it's just some number. Who cares what it is? It's a finite number. And I'll just put infinity minus a number, right? And then there's still this 1/2 in the front. So let's think. If you have infinity and you subtract some number, even if it's a billion, this is still going to infinity. And even if I multiply by 1/2, this is still going to infinity. So overall, my limit's going to be infinity, which means that this improper integral diverges, okay? Now, some of the students didn't switch around the order of subtraction. Let me just show you. The ones who didn't do this, they had a negative 1/2 in the front, and then they had a number minus infinity. So then they would just have that negative infinity times some negative number now goes to positive infinity. So either way, if you skip this step, you'll still get to the same final answer. You would just have, instead of this moment, let me write out what you would have had. You would have had negative 1/2 times some number minus infinity. And then you could say, okay, this is going to negative infinity times that negative 1/2. This would all go to positive infinity. So either which way you slice and dice it, you're ending up with the same limit. Okay? Very good. Very nice. One more improper integral. This one's more obvious that it's improper because we see glaring at us that negative infinity as our lower limit. So whew, that has got to go. Let's rewrite it as a limit. You want to use t still, or you want to switch it up? Yeah, let's still use t. I wouldn't use x. I just wouldn't, because x is usually a variable in our integrand. We don't deal with it like with the limits for improper integrals. Then we're going t to 0 z over, allow me to inspire you. Are you ready? Z squared squared, ooh, plus 4 dz. Yes, I cross my z's because otherwise it's too confusing with the 2's. And then when you get to multivariable, there's going to be z's running amok. So start crossing them now. Do you see what to do? I tried to inspire you. We're going to do u sub again. So we're going to let z squared be u. So u is z squared. Then du is 2z dz. You see how we have that? Z dz. So then 1/2 du is z dz. So we've got limit t goes to negative infinity integral. I'll switch the limits in just a hot second. Please give me a moment. We have 1/2 du over, that's right, u squared plus 4. And then my new limits, currently, who do they belong to? 0 and t belong to z. They belong to z. So I'm going to substitute them in and figure out my new limits in terms of u. So u of 0 would be 0 squared. That stays 0. And then u of t, that's t squared. So that's my new lower limit. How are we doing? Okay, good. So now let's see if we recognize what to do. This is limit t goes to negative infinity. Take that 1/2 out, please. T squared to 0 du over u squared plus 4. We've encountered this integral earlier, just with a little different numbers. Do you remember? It's our good friend tan inverse. Yes, please don't trig sub. You're wasting minutes that you won't get back. Limit t goes to negative infinity. Keep that 1/2. Then antiderivative here would be another 1/2 tan inverse u over 2, evaluated from t squared to 0. Beautiful. Beautiful. So what's going on now? Limit t goes to negative infinity. I have 1/4 tan inverse of 0 divided by 2 is still 0, minus tan inverse of t squared over 2. Good? Okay. So now let's think back. Tan inverse of 0, that's just 0. So that's gone. And then now I'm taking the limit as t goes to negative infinity of tan inverse of t squared over 2. So notice I have t squared over 2. So even though t is going to negative infinity, if I square it, now it's going to positive infinity inside this argument right here. This is all going to positive infinity. Dividing by 2 does nothing. It's still going to positive infinity, okay? So what is tan inverse approach as we head towards negative infinity? In this case, you need to imagine the graph. There's no other way around it, okay? So just knowing your basic graphs are so crucial. Tan inverse has horizontal asymptotes at pi over 2 and negative pi over 2. So as we go to positive infinity, tan inverse approaches, that's right, pi over 2. Not negative pi over 2. Some people got confused with that because this t is squared. So the argument's going to positive infinity. So we're going to positive pi over 2. If this t had not been squared, if it was just t, yes, then if t goes to negative infinity, this would all be negative infinity and you would have negative pi over 2. But that squared changed it all for us. So what's going on here? What am I left with? I've got that 1/4 minding its own business sitting outside calmly. And then 0 minus pi over 2. So if I clean this up, this is negative pi over 8. I don't care what number I get, just as long as the limit exists as a finite number, I can say this improper integral is convergent. Yay. I don't know, I get happy when they're convergent. And I feel slightly defeated when they're divergent, even though it's not like one is any better than the other. Anyways, how was that one? Yes, you have to know your graphs. You do. Okay, next problem, we have arc length. So find the length of the curve, y equals 1/6 x cubed plus 1 over 2x from x equals 1 to 2. So you got to know your arc length formula. Integral from a to b, square root. I can already tell I'm going to integrate with respect to x the way it's given. So I'm going to write 1 plus y prime squared dx. Or you could think of this as f prime or dy dx, whatever. I like to clean up and simplify all of this before I set up the integral, okay? So y equals 1/6 x cubed, and then please be careful right here. This is 1/2 x to the negative first. Leave the 2 in the denominator. It's not going to help you if you bring it up with the x to take the derivative. It will just make things worse, okay? So now let me take the derivative. Let me get y prime. Y prime is going to be 1/6 times 3x squared plus 1/2 times -1 times x to the negative second. I really went slowly here, hoping I don't lose anybody. So this is 1/2 x squared minus 1/2 x to the negative second. Good? Okay, now we're going to square the first derivative, the whole quantity, all of this. So then that's going to be, if you need to FOIL it and write it out twice and FOIL your little heart out, go for it. Otherwise, you should just know the pattern, right? When you square a binomial, you square the first term. So that would make it 1/4 x to the 4th minus 2 times first term times the second term plus, and then you square the last term, which would be 1/4 x to the negative 4th. And then this is, one of the classic little arc length problems where you're going to end up with a -1/2 in the middle, magically, because someone sat there and made sure it was going to happen, okay? So the 2 and the 1/2 cancel, and then the x squared and the x to the negative second cancel. Oh me, oh my, I just have a -1/2 here, plus 1/4 x to the negative 4th. And then one more thing I still need to do is add 1. So 1 plus y prime squared, 1 plus 1/4 x to the 4th, minus 1/2 plus 1/4 x to the negative 4th. I can combine 1 and -1/2, and I get positive 1/2. Very good. So 1/4 x to the 4th plus 1/2 plus 1/4 x to the negative 4th. And I wrote the plus 1/2 in the middle on purpose. Why would I do such a thing? Because I want you to look right here. You probably can't even see that yellow. I want you to look right here and notice that up above, we had almost the exact same expression. It's just one little baby thing is different. Do you see the one little baby thing? Now we have plus 1/2. Earlier we had minus 1/2. And remember, this little expression here came from squaring 1/2 x squared minus 1/2 x to the negative second. So that means this factors in precisely the same fashion. The only difference is that I will have plus between the terms now instead of a minus. So I can rewrite this as 1/2 x squared plus 1/2 x to the negative second squared. Good? And that's just like the classic trick that happens with a lot of arc length problems, okay? So why are we so excited that it factors like this? Because this whole quantity right here, that's 1 plus y prime squared, that goes underneath the square root in the integrand. So then we're set. The square root, the squared, they're going to cancel, and then we can just go about our lives and integrate. So now, arc length is going to equal integral. A to b was 1 to 2, and then we have square root 1/2 x squared plus 1/2 x to the negative second squared dx. All right. Square root and the squared cancel, so I just have 1 to 2, 1/2 x squared plus 1/2 x to the negative second dx. Some of them are so good, they take that 1/2 out. Yes, they do, from 1 to 2, and then you have x squared plus x to the negative second dx. Now we can go ahead and take the antiderivative. So I have 1/2 sitting out there. Antiderivative of x squared is 1/3 x cubed. x to the negative second. You're going to add 1 to the exponent and divide by the new exponent. So it'll be x to the negative first, dividing by that negative 1. Now I just have minus, let me write it as 1 over x right away, from 1 to 2. Okay, and then from here, yeah, we're going to continue simplifying. No calculator, just the one you were born with. So plugging in 2 cubed is 8, so 8/3 minus 1/2. Plugging in 1 for the lower limit, minus 1/3 plus 1. Yes? Very good. And then 8/3 minus 1/3, that's 7/3. So I have 1/2 times 7/3. And then negative 1/2 plus 1, that's positive 1/2. Okay, inside, what do we have? So inside, this is going to be 14 plus 3 divided by 6. So this is 17 over 6 inside, times 1/2 gives me 17 over 12. Are you curious how I got that 17 over 6 so quickly? When you have 7/3 plus 1/2, this will not give you the answer in the most reduced form always, but it's very slick and quick. Watch. You do 7 times 2, so 14. Keep the same sign, which is plus. 3 times 1, that's 3, over, and then you multiply the denominators together, 3 times 2, which is 6. 17 over 6. It will not always give you the LCD though, right? But at least you just get everything combined, and then you can reduce later if you want. It's very fast. Okay. How are we doing? Good. I love it. Now just mixed bag of integrals and then the surface area problems coming up. So evaluate the integral. We have cosine t dt over sine squared t minus 9 sine t plus 14. So u sub first, right? The denominator is quadratic in nature in terms of sine. I would love to get rid of that cosine in the top, so we can do that just by doing a slick little u sub. Let's let u equal sine t, and then du is cosine t dt. So we're going to have du over, now the denominator becomes u squared minus 9u plus 14. I think it's time for partial fractions. What do you think? Good. So u squared minus 9u plus 14, that factors into, yes, u minus 7, u minus 2. So both of those are just linear factors. I have a over u minus 7 plus b over u minus 2. Perfect. Let's multiply through by the LCD. So that would be u minus 7, u minus 2. Now on the left, I'm going to have 1 equals a times u minus 2 plus b times u minus 7. I'm going to show you a different way to solve for a and b than I did in question number 2, okay? Since I didn't have any factors that were irreducible quadratics, I can do this method. I'm going to let u equal 2. Why did I pick 2? Because that would make this factor equal to 0. So if I let u equal 2, I have 1 on the left equals a times 0 plus b times negative 5. Very good. So 1 equals negative 5b, which means b is negative 1/5. Cool? And then you can just repeat the process. Look back here. This time I'm going to let u equal 7. So then I have 1 equals a times positive 5, good, plus b times 0. That's why I picked 7. And then we have a is positive 1/5. Good? Okay, so then now I can rewrite my integral as 1/5 over u minus 7. b is negative 1/5, so I'm going to write minus 1/5 over u minus 2 du. Okay, let's talk from here. Don't put the 5s in the denominator. It will make life worse, because then if you have 5 in front of u, when you take the antiderivative, It's going to involve ln, but then you're going to have to divide by 5 again. We don't like constants in front because then it's going to, require another u sub, or you're just going to have to think about it and divide. So don't do that. Don't do that. What's the slickest way to go about this is please just take the 1/5 out of the whole integral. Do you see how much better life will be? 1/5 sitting out here, minding its own business, allowing us to just integrate in peace. I mean, it's hard enough as it is. Let's not make our lives any harder, okay? Look at that. Oh, now I'm not even stressed about the 1/5. There he is. Antiderivative of 1 over u minus 7. Yes, ln, absolute value, u minus 7. Minus, good, one more, ln, absolute value, u minus 2, plus c. And then you know what mistake I saw a lot on this problem? They stopped here. They rejoiced that they made it thus far and they forgot to go back to the original variable. And I know they know better. It's so funny. So we have here 1/5 ln. Do you remember who u was? Sine t. And I do need to keep absolute value because this could definitely be negative. Minus ln absolute value sine t minus 2 plus c. Okay? You can stop there. I don't care. You can distribute the 1/5. I don't care. You could use log properties and combine. Some of them did that. Whatever. Have at it. You just have to at least be back in terms of the original variable to get full credit on the problem. Okay? Good? Yeah, a lot of people did that one fine. Here's another one. Surface area problem. I did tell them this was going to be on the test. I did. It was straight from the homework. And I said, this is such a lovely problem. I'm putting it on the exam. A few didn't hear because they came in late for the day. So it showed. Okay, find the area of the surface generated by revolving the curve about the indicated axis. So here's our curve. They give me the bounds. And since we're spinning around the y-axis, then that tells me how my surface area formula is going to be set up. So surface area, I want the dark blue. Surface area is going to be 2 pi integral a to b. If we're spinning around the y-axis, then my radius is going to be x. And then we have ds. ds is a little piece of arc length. And in this case, since we have x as a function of y, then ds is going to be square root 1 plus dx dy squared dy. That can change up, okay? If you're going to take Calc 3, get used to working with ds and knowing that that means a little piece of arc length, okay? So let's write out x is square root of a squared minus y squared. Now, a is just a constant, okay? I'm going to find the derivative, dx dy. And I encourage my class to use this little shortcut. When you take the derivative of a square root quantity, to just kind of save some steps with the chain rule, you put 2 and the original radical in the denominator. So you have 2 rad, ooh, so ugly, excuse me, 2 rad a squared minus y squared. And then you put the derivative of what's underneath in the numerator. Derivative of a squared would just be 0 because it's a constant. And then derivative of negative y squared would be negative 2y, okay? That's the part people forgot the most, the chain rule, sadly enough. Okay, so these 2's cancel, and then we just have negative y over rad a squared minus y squared. So that means dx dy squared would be y squared over, now no more radical, a squared minus y squared, okay? Okay, so from here, let me just add 1 and get everything set up. So 1 plus dx dy squared would be 1 plus y squared over a squared minus y squared. If I get a common denominator, this becomes a squared minus y squared plus y squared over a squared minus y squared. You see how these y squareds cancel out so beautifully? Ugh, I love it. So then this is just a squared over a squared minus y squared. Good. So now we're ready to put everything together. Surface area is going to be 2 pi. Limits a to b are going to be 0 to a over 2. Now I'm integrating with respect to y. You're not in multivariable calculus yet, so you're not going to put x in your integral when you're integrating with respect to y. No, you're going to replace x with, yes, rad a squared minus y squared, right there. So you're going to have rad a squared minus y squared times, and then I have square root of 1 plus dx dy squared. Square root of all of this right here. Let me color code for you just a wee bit more so you can see what's going on. 1 plus dx dy squared is right here. So I have square root of all of that tacked on. Square root of a squared over a squared minus y squared dy. Good? Okay, from here, the problem's just going to flow. So we have 2 pi integral 0 to a over 2 rad a squared minus y squared. We can split up the radical over the numerator and denominator. So I have rad a squared over rad a squared minus y squared dy. Oh, do you just love this moment right here? The rad a squared minus y squared cancels. Rad a squared, I know it's just going to be positive a because we're from 0 to a over 2. Perfect, perfect. So I have 2 pi integral 0 to a over 2, just a dy. A is just a constant. Pretend it's 5. What would antiderivative of 5 be with respect to y? 5y. So antiderivative here is ay. So 2 pi a y from 0 to a over 2. These limits get plugged into y. 2 pi a can stay out of the party. Sorry, 2 pi a, you're not invited. We have a over 2 minus 0. So you just have 2 pi a times a over 2. The 2's cancel. And final answer is pi a squared. Lovely. Just lovely. Okay. Nearly there. 2 more. Evaluate the integral using any appropriate method. We have integral from 1 to 4, rad y, natural log of y, dy. Anything jumping out at you? Yes, it's time for some by parts, exactly. Because u sub would not work. There's nothing I could let equal u and then I would have du sitting there. So especially the natural log clues me in. It's probably time for some by parts. So we're going to need to pick u and dv. And most of the time when there's natural log in a problem, that's what you let be u. So u is going to be natural log of y. dv is rad y dy. But you know what, guys? I'm going to already write it as y to the 1/2 dy. Okay? So now let's find du. That would be 1 over y dy. And v would be 2/3 y to the 3/2, right? Add 1 to the exponent, divide by the new exponent. So let's see what we've got now. We have uv, which I'll write as 2/3 y to the 3/2 ln y. This gets evaluated from 1 to 4. Minus integral from 1 to 4 of v du. So that's going to be 2/3 y to the 3/2 times 1 over y dy. All right, I'm not going to evaluate the first part just yet. Let's just save it and we'll do it all at the end together. Okay. Let's take this 2/3 outside the integral. Why are we leaving it there? That was not good. 1 to 4. Now I can simplify y to the 3/2 divided by y, just subtract 1 from the exponent. So now it's going to be y to the 1/2 dy. Okay, we can take that antiderivative, no big deal. So I'm just going to put everything in the next step all together. Watch, 2/3 y to the 3/2 ln of y. I'm not going to write from 1 to 4 because I'm going to put it at the very end for everybody. So minus, we already have that 2/3 hanging out. Antiderivative of y to the 1/2 would be y to the 3/2, and I'm going to pick up another 2/3 from 1 to 4. All right, let's start plugging in our limits. And this, you know, is 4/9, right? We don't need to waste time rewriting all of that. So we have 2/3 times 4 to the 3/2, natural log of 4, minus 4/9 times 4 to the 3/2, minus, I'm plugging in 1 now, 2/3 times 1 to the 3/2 times ln of 1, and then this would be plus 4/9 times 1 to the 3/2, which is just 1. Okay, nearly there. So what's this? 2/3, 4 to the 3/2. So we did a 3/2 exponent in the first question. You take the square root of 4, that's 2. Then you raise it to the third. Now it's 8, very good. Times ln of 4 minus 4/9, yep, that's 8 again, minus, now ln of 1 is 0, so this whole term's 0. All of this, goodbye. That's 0, plus 4/9. Okay, very good. So what is this here? 16/3, natural log of 4. This is minus 32/9 plus 4/9. So that's minus 28/9. If they made it this far, I gave them full credit. I certainly did. But some students just had that je ne sais quoi, extra zhuzh to their work. And they said, Professor V, ln of 4 is ln of 2 squared, isn't it? Why, yes, it is. And then they just moved this 2 in the front and made it 32/3 natural log of 2 minus 28/9. That's really the most simplified answer. I didn't deduct points, though, or whatever, if some students stopped there. I was rather proud of them. But the ones who took it that extra step, oh me, oh my, they are just too fabulous. Good job. Okay. And then one last question, which honestly, I meant to be the freebie of the whole exam. I figured they're tired. It's the end. They've seen it. It was on their practice test. Oh, so many of them got it wrong. It made me sad. But don't worry. Overall, the scores were fab. Can you see what to do? I wanted it to be just a relaxing little problem. Let me rewrite the integral for you. Dx over 2 rad x. 1 plus, think of x as rad x squared, okay? That's the key. And then you're just going to do a u sub. You're going to let u equal rad x. Du would be 1 over 2 rad x dx, which we have right here. That's du. Rad x is u. Can you rewrite the integral in terms of u now? I think so. You would have du over 1 plus u squared. Who's that? We know that antiderivative. That's tan inverse of u plus c. Tan inverse of rad x plus c. That is it. Okay. Okay. I did put an extra credit problem. I did. I don't do partial credit though for extra credit. It's all or nothing. So it's got to be perfect or they're done. So evaluate the integral. This one looks scarier than it is. The key is we're going to split it up into 2 integrals right off the bat. So we have x plus 7 squared tan inverse of 3x over 9x squared plus 1 times x plus 7 squared dx plus, and then the other 2 terms, 9x cubed plus x, I'm going to put separately, over 9x squared plus 1 times x plus 7 squared dx. Okay. This problem was also on their practice test. So here we go. Integral 1 and 2. 1, 2. Okay. Can you see already integral number 1? Some loveliness is going to happen. That x plus 7 squared cancels. Yay. And then you have integral tan inverse of 3x over 9x squared plus 1 dx. Do you see what to do? Just a u sub, yeah. You're going to go ahead. Let's let u, I'd like a light blue. Let's let u equal all of this, tan inverse of 3x. So du, the derivative, would be 1 over 1 plus 3x quantity squared is 9x squared. And don't forget, you have to do the chain rule. You have to multiply by the derivative of 3x, which is 3. So notice here, all I have is 1 over 9x squared plus 1. So that means 1/3 du is 1 over 1 plus 9x squared dx. So now we're ready to proceed. So we have here 1/3 integral u du, which is going to be 1/3 times 1/2 u squared plus c1. So this is 1/6. U was tan inverse of 3x squared plus c1. Okay, there's the first part. Done. Let me number. This was integral number 1. And then now let's move on to integral number 2. Let me copy it. And you can see here, the numerator still factors further. Did you catch that? Good. You can take an x out, and then you have 9x squared plus 1. So that's key, because then that'll cancel with the 9x squared plus 1 in the denominator. And then all we have is x over x plus 7 squared. Now from here, you could totally do partial fraction decomp. Or, I like showing them my little slick trick. You just do a little plus and minus manipulation, and you don't have to do partial fractions. So I go, oh man, I wish there was a plus 7 in the numerator. Well, I'm going to make it happen. But if I just randomly add 7, I must subtract 7. You can't just go willy-nilly adding and subtracting numbers without any rhyme or reason. So I'm going to put x plus 7 minus 7 over x plus 7 squared dx. And then the whole point of doing that is so that you group things together. So you're going to have x plus 7 over x plus 7 squared minus 7 over x plus 7 squared dx. And then here, this is going to cancel, right? Boop, you're gone. This is to the first. I just have a 1 in the numerator. 1 over x plus 7 minus, this I can integrate no problem. If you want to write it as x plus 7 to the negative second, that might be helpful. Dx, and then this, yep, ln, absolute value, x plus 7. I'm going to add 1 to the exponent, divide by the new exponent. That'll make this a plus 7. I'm just going to hop to it and write it over x plus 7 plus c2. Okay, so that's the second part. Done. And then all together, what do we have? We have 1/6 tan inverse of 3x, this part's squared, plus ln, absolute value, x plus 7, plus 7 over x plus 7 plus c, where c equals c1 plus c2. Okay, that's it. Hope you enjoyed the exam. Like I said, I can't give out specifics, but they did really, really well for the most part. Lots and lots of A's. So I was very happy. The way I give my exam questions, I give the students a study guide and I pull the questions straight from there and from the assigned homework problems, and I just change up the numbers ever so barely. So these problems they've all seen before. Nothing was a shock. Even the extra credit, they'd seen it. But yeah, the ones who practiced diligently did so well. I'm so proud. And I have an old Calc 3 exam that I'll solve for you guys next. since some of you really enjoy watching me solve exams that I give. And I don't mind having it publicly posted because I always write a new test every semester. So it's not a problem for me. And I'm happy if my current students can watch this and benefit too. That way they can see where they messed up on the test and then learn from it for next time. So that's it. If you stayed till the end, leave me a comment down below. What a trooper you are. It's Saturday, so I'm going to ride my Peloton and then go to hot yoga. That's the routine for this morning. And I hope you all have a lovely weekend. Give the video a thumbs up. Subscribe if you haven't already. And then if you need to review any of the topics that were covered in this video, they're linked all in the description. I also have all my videos organized into playlists on my YouTube channel for Calc 1, 2, 3. Or if you need to review, there's pre-calc, trig, and algebra, all that good stuff. And you can follow me on TikTok and Instagram and Twitter, Math with Professor V. Please follow me on TikTok. I want to get up to 10K ASAP. Okay? I love you all. I'll be back soon. Bye.